Okay, this is our lesson on how to calculate the speed of sound. We'll start off just with a little clip I've found with a quite amazing lightning strike just to demonstrate the point. And the idea is, how could you check if this lightning storm was about 200 miles away? See if I just flick over to the video and play it.
A big apple strike last night.
Okay. So if you notice, there is a flash of light first, and then everyone kind of hears the sound shortly afterwards. So this is sort of what we're dealing with today as to how can we work out the speed of sound if we're in some kind of a lightning storm, and what information would we need to know, how would we do it, etc. Okay, so quick aims then. We're going to describe how the speed of sound can be measured, we're going to describe the problems with this measuring ideas, and we're going to suggest how to improve the experiment maybe. Alright, so the general idea, light travels very fast. We mentioned it last lesson, 300 million meters per second. It can go around the Earth nearly 8 times in a second. So if you think about a second, there you go, it went around the Earth about 8 times in that amount of time. Sound is much more slowly. We did meet this in some calculations last lesson. It's still pretty fast, but how could we work out just how fast? So the experiment that you could do would look something like this. You would get 2 blocks of wood, and you could stand at a distance apart, so the one end of the playing field is what we sometimes do at school, and you would start the watch as soon as you see the blocks hit together. So one person stands one side of the field, one person stands the other. The person with the blocks bangs the blocks together. The person with the stopwatch on the other side of the field starts the stopwatch as soon as they see the blocks hit. So it's going to look like something like this from the person's point of view. So, okay, as soon as they see them hit, they start the stopwatch. There we go, the blocks have hit, but then, there we go, that noise, they stop the stopwatch as soon as they hear the sound. So from the person on the other side of the field who's watching the person hitting the blocks together, it's going to feel something like this. They start the stopwatch, now, they wait, and they stop the stopwatch as soon as they hear the sound of the blocks hitting. And they could end up with a set of results like this. So they could try to 80 metres, do it 3 times, 100 metres, 3 times, 120 metres, do it 3 times. So we need to calculate the mean. Well, first, do you think we've got any anomalous results? If we have a look, it looks as though we've got an anomaly here. This 0.1 is much lower than the other 2 tests, so we would not include that in our mean. So let's calculate the means. We just go that plus that divided by 3 gives us a mean of 0.26. For the 100 metre line, 0.30 plus 0.32 plus 0.34. Add them up, divide by 3 gives 0.32. This is our mean, so we don't want to include that in our mean. So we go 0.38 plus 0.39 divided by 2. I've rounded it up to 0.39. Using our equation, we can just work out speed. We'd say speed is the distance divided by the average time, and we could come up with 3 values for speed. So what measurement affected the most how close your answers are to the actual value of sound? I'm pretty sure we could measure the distance pretty accurately. We could use a tape measure, but this measurement of sound relies on humans, and humans tend to have something called a reaction time, and that leads to errors, and they're random errors in our experiment. So measuring the time is the hardest in this particular experiment. What we could do, we could use a more high-tech method, so we could do exactly the same. But this little box here, if you hit a hammer against a metal plate near to this microphone, then this microphone picks up the sound first, the sound waves travel into this microphone, and the difference in the time, you can work out the speed if you know the distance between these two. So it is exactly like we've just talked through doing with 2 humans on a field, but it's a little computer that can do it for you. And you might have seen this used in school, and it comes up with much better answers because you haven't got a human measuring the time difference. And as well as that, you don't have to separate these by tens or hundreds of meters. You can literally do it from one side of the bench to another. Okay, so this leads us to, well, what is the accepted value? If you look on Wikipedia or anything, it's 343.6 at 20 degrees, which is about 770 miles per hour, or 1,237 kilometers per hour. But what we tend to learn in physics is an accepted value of about 330 meters per second. It's much easier to remember, but people do get confused and start remembering that the speed of light is 3 times 10 to the 8 meters per second, or 300 million, and obviously sound doesn't travel that fast. It travels fast, but not that fast. Okay, so just a little bit to expand our thinking. A student performs the following experiment to calculate the speed of sound. What is the calculated speed if it takes 0.32 seconds for the person to hear the echo? If they stand 50 metres off the wall, we need to do a speed equals distance divided by time, but be very careful. The distance isn't 50 metres because it's gone there and back. If you do this experiment on your own in front of a wall, it's different to the two people at either end of the field because you need to measure the distance to the wall, then double it for the distance of the sound that has travelled. So 50 times 2 is 100 divided by 0.32 gives us a speed of about 312.5 metres per second. So you can do the experiment on your own, but you need to remember to think carefully about the distance that you're measuring. Okay, some questions we'll just talk to. Do you think it was important to measure the distance very precisely? We mentioned earlier we don't think so. The distance to the nearest metre would be absolutely fine. The problem is the times. The times we're measuring are much smaller, so the time is where the error creeps in to our calculations. Apply your understanding of the errors in this experiment to explain why high-tech apparatus might give better results. As we've mentioned, human reaction time gives us quite large random errors. If we use high-tech apparatus recording equipment, that gives you a much better answer. Okay, the next two questions we'll deal with on two separate slides. So here's the first one. So link the answer to how far away lightning is. If it takes 6.5 seconds for thunder to reach you, write a general rule for anyone in a thunderstorm. So distance is speed times time. We know that the speed of sound is 330 metres per second. If it takes 6.5 seconds, that's 330 times 6.5 is about 2,145 metres or 2.1 kilometres. So a general rule might be if 2.1 kilometres is 6.5 seconds, approximately each 3 seconds that pass means the storm is 1 kilometre away. So you could say count the seconds and each 3 seconds is 1 kilometre is a nice quick rule. And finally, the moon is 384,400 kilometres away. How long would it take sound to get there if it was possible? We know that space is a vacuum with no particles, so a longitudinal wave can't travel. To do some revision, how long does it take light? Let's do these. Time is distance divided by speed. I've just rearranged our speed equation. For sound, the distance is 400, and then we need 3 extra zeros because remember this is 384,400 kilometres, so this is 384.4 million metres. Divide that by the speed of sound, which is 330, and that gives us a big answer, over 1 million seconds. If we convert that into days by just divided by 60, divide by 60, divide by 24, we end up with 13.5 days, so quite a long time for sound to get from the moon. And then finally for light, we did do this, we talked about the speed of light in the last lesson, 384,400 kilometres in metres divided by the speed of light gives us a much shorter time of 1.3 seconds.